Hello, everybody. My name is Zach Vig, and I'm a PhD student at the University of Maryland. And I'm here to talk to you guys today about the coolest silicic domes in the solar system, the Gruithuisen domes. And more specifically, I want to talk to you guys today about why we think there could be olivine present within the silicic material that makes up the domes. So I don't think I have to explain to you guys why the Gruithuisen domes are important. I think Carrie Donaldson-Hanna did a wonderful job of that this morning. But what I will say is that the Gruithuisen domes are first and foremost an exemplary lunar red spot. And the reason I say this over a silicic volcanic complex is because until we go there, they really are defined by their spectral uniqueness. After all, they were first discovered in 1972 using telescopic observations and have since been covered by numerous spectral data sets. And today we would like to use a lot of these spectral data sets in the visible near infrared range to address kind of the flip side to silicic volcanism, and that is the mafic component that we think is also present on the surface. So this project really started when we started looking at this data set that is often underutilized because it is so scarce, and that is the Moon Mineralogy Mapper, or M-cubed, targeted mode data set. But fortunately enough for us, there is a pass of M-cubed in targeted mode directly over the Lunar Vise landing site on the Gruithuisen Gamma Dome. And what we started off doing is making a standard kind of RGB composite that is standard for M-cube data, where the 1 micron band depth is in the red channel, the 2 micron band depth is in the green channel, and the albedo is in the blue channel. And the thing that we noticed from this image were these yellow splotches that popped up on the dome. And typically yellow kind of means more mafic material. So we took a look at these spectra, and they matched pretty closely with the mafic mineral olivine. Particularly, they had a 1 micron band center that was a little greater than 1 micron, roughly 1.1. And they also showed a lack of a lack of a strong 2 micron band. So great, that's good and all, but now we wanted to know, where does this olivine actually exist in the domes? So what we used is some spectral classification algorithms here. We're showing a spectral angle mapper result, which we kind of interpreted using spectral parameter maps, such as the 1 micron band position map. And we were able to determine that this green unit right here is related to the olivine. It is the olivine. And from this map, we showed that really the olivine only exists on the kind of steep slopes of the Gruithuisen Gamma Dome and a little bit in the Northwest Dome. Okay, great. But the story does not end there, because as good scientists, we went out and gathered more data. And lucky for us, alongside the M-cubed targeted mode pass, there's also 2 passes of M-cubed in global mode, which is just a binned version of the targeted data. And we also have several passes from the Kaguya multiband imager and the Kaguya spectral profiler. And the thing I'll say about these data sets is that besides being from slightly different spectral ranges and slightly different spectral resolutions, they are also taken at different spatial resolutions and at different viewing geometries. So to kind of illustrate how different these data sets really are, I mapped out each of the single pixel sizes of these instruments on the wonderful WashU campus here. And you can see that going from, MI to M-cubed to SP, they really are looking at physically different things, i.e., a geological phenomenon that appears on the scale of this grassy area out here might not appear on the scale of 2 baseball fields and a football field, for example. So now let's get into our comparison. So the thing that really stuck out to us when comparing these data sets is that there seems to be a discrepancy between the 2 M-cubed global data sets and the rest of the data sets. Particularly, the M-cubed global data sets do not show any 1 micron absorption, whereas the other data sets do, despite being different spatial resolutions. So we knew pretty early on that this really isn't just a problem with spatial resolution, it's probably something else. So the next thing we looked at is viewing geometry. Specifically, we first looked at local solar incidence angle, which is essentially just how high the sun is in the sky when the instrument is viewing the ground. And we found that the M-cubed global data sets were taken at a lower solar incidence angle, so the sun was higher in the sky than the M-cubed targeted data set and the Kaguya SP data sets, which show the highest 1 micron absorption. But throwing a wrench into things, we have the Kaguya MI data set that shows a 1 micron absorption, but is taken at a similar incidence angle to the M-cubed global data sets. So it's not an incidence angle problem thing. It's probably something that's a little more complicated. And we're going to have to look at something like the solar azimuth angle as well, like how the sun is actually coming in and looking at the scene. And one way that we want to try to look at this a little bit closer is by making high resolution illumination maps of the very specific ROIs where we see the olivine. And to kind of motivate why we'd want to do something like this, this is a visible image from the Kaguya terrain camera, and it really shows well that this hillside right here, where we think we see the olivine, is kind of has this like rough, hummocky texture. And we think that some of this sub-pixel scale roughness might be affecting what each spectrometer is seeing at these different viewing geometries. So for example, this is an illumination map, and you can see that these craters right here at low solar incidence angle have these bright spots. But as you downsample to M cubed spatial resolutions, they kind of just get washed out. So, all right, great. We have some mafic material maybe, but really we have to take a step back and say, what is it even doing there in the first place? And to try to answer this question, I will bring up that there are two main theories for how the domes are created right now, and that is by basaltic underplating, melting creep-rich crusts, or by silicate liquid immiscibility after extensive fractional crystallization. And in both of these scenarios, you have to have a significant amount of basaltic melt in the system. And turning to terrestrial analogs, they suggest two kind of ways to bring this mafic material actually up to the surface so we can see it. And the first one is by mafic inclusions, whether it's mafic restites, where the silicic magma material melts the country rock that's more mafic around it and erupts it to the surface, or it could be a co-magmatism type of situation where you have the silicic magma and mafic magma erupting side by side in a bimodal volcanism scenario, like we see with the rhyolite domes in Iceland, for example. So, but the big picture question here, right, with all this, whether or not we have mafic material, really, can we use this mafic material to answer the big question of, can we constrain the formation mechanism of the Gruithuisen domes? And I think the answer is yes, in three very specific ways. The first is that I think this can improve silicic volume estimations, because current estimations assume that the entire domes are silicic material, but if there's a significant amount of mafic material, this could reduce the volume estimations, making things like silicate liquid immiscibility a little more plausible. The next is we could try to figure out the eruption mechanism, because if we can figure out this geometry problem that we're looking at, we can maybe see if this mafic material is pyroclastic or blocky material or something else entirely. And then lastly, we can go and look at other red spots in the moon and see if this mafic material present is something that's unique to the domes or if it's a more widespread phenomenon. So with that, I'll leave up a little bit of a summary of what I talked about, and I'll open the floor to questions. Thank you very much for listening.
Time for one quick question.
Yeah.
Fragile. Do you think the olivine is iron rich or magnesium rich?
I think did I grab the wrong one? I can't say for sure yet, but I think it's magnesium rich. That is the next step in our analysis, is to get a little more, like, constrain the chemistry of the situation. But yeah, we ran into this geometry problem that was kind of tripping us up. So